The lamp beside you is already in the past. What reaches your eyes right now is not the lamp as it is. It is the lamp as it was, a sliver of a moment ago, when this light first left it and started toward you. That delay is almost nothing. A few billionths of a second to cross a small room, far too small for anything in your body to feel. It is not zero. For almost all of human history, the most careful minds alive were sure that it was. Sure that seeing was instant, that the world simply arrived the moment you turned to look, and they had every reason to think so. How do you come to believe that light runs late, when no one has ever once caught it moving? Light is fast enough to circle the entire Earth about 7.5 times in a single second. Not a beam fired straight out into space. Around the curve of the planet and back to where it started, 7.5 full laps before you could finish saying the word once. A speed like that has no business feeling slow, and in ordinary life it never does. It feels like nothing at all, like the complete absence of any weight. You flip a switch, and the far wall is lit in the same heartbeat your hand moves. The room does not pause to let the light catch up. The first strange thing comes before any of the history, before any of the names. We call that speed a limit, the fastest that anything in the universe is permitted to move, a ceiling built into the structure of reality that nothing has ever been seen to cross. A pace that quick, and we treat it as a wall. Start with how the delay manages to hide. Across a small bedroom, the light from the lamp reaches you in something like 20 billionths of a second. Your body has no way to register an interval that short. When something startles you and you flinch, the signal running from your eye to your brain and back out to your muscles takes about 0.2 of a second. That flinch, the quickest your nervous system can manage, is roughly 10 million times longer than the time the light needed to cross the room. The light was late. You were far later. By the time you registered anything at all, the lateness of the light had already been swallowed inside your own. It sits buried the way a single grain of sand sits buried in a mile of beach. Still there, still real, simply too small against everything around it to ever be picked out by hand. Measured with the eye alone, the delay does not round down to almost nothing. It rounds down to nothing. There is a temptation to look back at the people who lived before this was understood and feel a little superior, and it falls apart the moment you take their position seriously. They concluded that light arrives the instant you look, because that is exactly what every measurement a human body can make reports back. With no instrument finer than the eye, instant is not a careless answer. It is the honest one. Nothing in plain experience so much as whispers that the light might be running behind. Stretch the distance, though, and the hiding begins to fail. The moon is far enough away that its light takes about 1 1/3 seconds to reach you. The full moon you look at tonight is the moon as it stood a little over a second ago. The sun is farther by a long way. Its light needs around 8 minutes to arrive, so the sunrise warming your face already happened. 8 minutes gone, while you were still in the dark. The delay was always present. It only needed enough distance to grow large enough to catch. 8 minutes is enough to unsettle anyone who follows it through. If the sun were to go out right now, you would have no warning at all. You would keep feeling its warmth and keep seeing it sit calmly in the sky for a full 8 minutes after it was gone, living inside a version of the sky that no longer existed. Put a number on the speed itself. In empty space, light covers about 186,000 miles every second, close to 300,000 kilometers, fast enough to carry you 3/4 of the way to the moon in the time it takes to say the word once. And in every direction anyone has looked since, at every scale, that same speed turns up unchanged. Light from a candle on your table, light from a star tearing itself apart on the far side of the galaxy, light from the most distant edge we can detect. All of it travels at one fixed pace, and nothing carrying mass has ever been clocked going faster. We have spent enormous effort trying. In the largest machines ever built, single particles are driven to within a hair of that speed, a fraction of a percent below it. Pour in more energy, and they creep closer and closer, and the final sliver simply will not close. The particle grows heavier instead of faster, hoarding the energy rather than spending it on speed. The wall holds every time. Set that against everything your hands have taught you. A car will always go a little faster with a stronger engine. A ball thrown harder flies quicker. Nothing written into a highway or a fastball says this far and no further. Speed, in every object you have ever handled, is open at the top. The universe does not agree. Underneath all of it runs a single fixed pace that light keeps and nothing beats. And that pace refuses to bend for more energy, more force, or more wanting. The part that surprises me most is that the ceiling does not really belong to light. Light only travels at it because light has no mass to hold it back. The limit sits deeper than light, built into how cause and effect are allowed to reach from one place to another at all. Nothing you do here can touch anything over there sooner than light could carry the news. The universe places a delay on consequence itself, and light is simply the most familiar thing we have that runs flat out against that ceiling. A universe could have been built with no such limit, with speed open at the top the way your intuition keeps insisting it should be. This one was not. If the universe does enforce a single top speed, why that limit and not another? And why a limit at all? On a clear night in the 1st January of 1610, Galileo pointed a small handmade telescope at Jupiter and saw 3 little stars he had never noticed, sitting in a neat line beside the planet. He wrote them down and thought little of it. The next night, they had moved. A few nights after that, there were 4 of them, and they had quietly shuffled their order. Stars do not do that. It took him several nights to accept what he was seeing, and once it landed, the answer was not subtle. Those 4 points were not stars. They were worlds, circling Jupiter the way the moon circles us, swinging from one side of the planet to the other on a fixed schedule. For the first time, a person was looking at a center of motion that was not the Earth. Until that week, every model of the heavens assumed everything turned around us. Here was a counterexample that anyone with a tube of glass could check for themselves. Something out there was orbiting something else, and it had never asked our permission. Those 4 moons keep remarkable time, and the reason is worth pausing on. Their orbits are locked into a simple rhythm. The innermost moon completes 2 laps for every single lap of the next one out, and that one completes 2 for every lap of the next. A gravitational lockstep that has held them in step for billions of years. A system that regular behaves almost like a piece of clockwork bolted into the sky, and that regularity is the thread the rest of this story will eventually pull on. For now, hold on to one fact about it. A clock is only useful if you can trust when its hands are pointing. That much, the new worlds and their steady rhythm, is the famous part, the piece that reached every history book. The stranger thing went unnoticed for another 60 years, and it was hiding inside the very same image. Galileo was not seeing those moons where they were, he was seeing them where they had been. Light from Jupiter does not arrive the moment it leaves. Depending on where the 2 planets sit along their orbits, it spends roughly 40 minutes crossing the gap. Sometimes a little less, sometimes closer to 50. So the arrangement of moons he sketched so carefully was already out of date the instant his pen touched the paper. While that light had been on its way, the moons had kept moving, sliding toward positions he would not lay eyes on for hours yet. He was mapping a past that felt exactly like the present, with nothing in the image to betray the difference. Widen that out, and the whole night sky stops being a picture of a single moment. The moon you see left a little over a second ago. The planets, minutes. The nearest stars, years. The faint smudge of a distant galaxy is light that set out before anyone alive was born to look up at it. Every point you can see is showing you a different slice of the past, all of them piled together into one apparent instant on the inside of your eye. The sky is not a photograph of the universe. It is a stack of different ages pressed flat and pretending to be one. There is no single moment the sky belongs to, because its light arrives sorted by distance instead of by time. That is unsettling enough out there. The reasonable reply is that none of it touches the present you are actually sitting in. The sky can be a collage of old light, and yet right here, in this room, now is plainly now. The lamp, your hands, the small sound of your own breathing. Surely these are simply happening, all at once, as you experience them. The present you feel is not handed to you ready-made. Your brain assembles it. Light reaches your eyes almost instantly. Sound crawls in far slower. A touch on your foot has to travel a longer nerve than a touch on your cheek and arrives a measurable beat later. If your brain reported each of these the moment it came, the world would feel smeared and out of sync with itself. Instead, it waits. It holds the incoming signals together for a brief window, around 0.08 of a second, shorter than a single blink, then releases them as one tidy, unified moment. The brain does more than synchronize. It predicts. Because it knows it runs late, it projects the world slightly forward, guessing where a moving thing will be by the time you act, so that you can catch a fast ball or step back from a falling glass, despite the delay built into your own wiring. The present you feel is partly a memory of signals that just arrived and partly a forecast of the instant about to come. You are not standing in the moment. You are standing in your brain's best reconstruction of it, dated a fraction of a second behind, smoothed over so well that the seam never shows. I have tried more than once to catch the exact edge of my own present, the line where the next instant turns into the one I am in, and there is no edge there to find. It slides away each time I reach for it, because the thing reaching is the same machinery that builds the present in the first place. The ruler and the thing it measures are cut from the same cloth. So the sky keeps no shared moment, sorted as it is by distance. And the body holds no fixed present either, built as it is by an organ that lags and stitches and guesses. Two completely separate reasons, one at the scale of planets and one at the scale of nerve fibers, arrive at the same quiet verdict, the single universal now that feels so obvious, the instant you assume every person and every star is sharing with you at this exact second, may simply not be something the universe keeps anywhere. Two people standing in different places, watching the same distant event, will not even receive it at the same time, and neither of them is wrong. Galileo never suspected any of this. He believed he was recording the heavens as they truly were, in the living present, and the record was already history before it dried on the page. The gap between what he saw and what was so would not be explained for 2 more generations. When the explanation finally came, it would not arrive from staring harder at the stars. It would arrive from a clock, and from a problem that had nothing to do with the sky at all. If your sense of now is built by a nervous system that lags and fills in, and the sky overhead keeps no shared instant at all, is there any now the universe itself agrees on? Picture a wooden ship 1,000 miles from any coast, somewhere in the 1600s. The captain can tell you, with real confidence, how far north or south of the equator he is. He cannot tell you, to save the lives of everyone aboard, how far east or west he has come. One of those numbers the sky gives away for free, the other it guards completely. North and south come easy because the sky is built around them. The Earth's axis points almost exactly at one star, and the height of that star above the horizon is your latitude, read straight off the heavens with a simple angle through a cross-staff or a sextant. Climb toward the pole and it rises. Sail toward the equator and it sinks. By day, the noon sun does the same work. The sky hands you your north-south position without asking anything in return, because that position holds still against the turning stars. East and west refuse to play along, and the reason is the very thing that makes a day a day. The Earth spins, and as it turns, the whole sky wheels overhead, the same stars rising and setting in the same arcs, no matter where along your circle of latitude you happen to stand. Sail 1,000 miles east, wait for nightfall, and the sky looks just as it would have 1,000 miles back. The rotation smears every east-west landmark into the same nightly parade. There is nothing fixed up there to say you are here and not there. If space cannot tell you your longitude, time can. The Earth turns a full circle, 360 degrees, in 24 hours, which comes out to 15 degrees of turning every hour. Noon, the moment the sun stands highest, sweeps slowly westward across the world. When it is noon where you stand, it is already afternoon to the east and still morning to the west. So your longitude hides inside a comparison. Take the difference between your local time and the time at an agreed home port at that same instant. Multiply by 15, and out comes your distance east or west in degrees. There is a quiet asymmetry buried in all of this, and it is stranger than it first sounds. Latitude has a natural zero. The equator is not a human choice. It is the one circle the spinning Earth draws for itself, exactly halfway between the 2 points its axis runs through. Longitude has no such gift. Every line of longitude is identical to every other, so there is no natural starting line, no place the planet itself marks as east-west zero. Someone simply had to choose one, declare a home meridian by agreement, and ask the rest of the world to measure from it. North and south were written into the Earth. East and west had to be invented. The relationship between time and place is tight enough to be merciless. A clock wrong by only 4 minutes throws your position off by a full degree, and a degree near the equator is about 70 miles, a hard distance to be mistaken about when there are rocks somewhere ahead in the dark. Be off by an hour, and you are off by 15 degrees, better than 1,000 miles, an ocean's worth of error folded into a watch that ran a little fast. Which drops the entire problem onto one brutal requirement. To compare your time with home, you have to know home's time while standing in the middle of nowhere. You have to carry it with you, a clock set in port that keeps perfect time for weeks, through pitching seas, swinging temperatures, salt air, and the slow corrosion of everything mechanical on a moving deck. In the 1600s, no such clock existed, and to most people it seemed there never could be one. The finest timepieces on land were temperamental enough. At sea, they were hopeless. There was, in principle, one other way to carry home's time without a clock at all. The moon drifts against the background stars a little each hour, slow but steady, like the single hand of an enormous dial hung in the sky. Measure the angle between the moon and a known star precisely enough. Compare it against tables computed back home, and you could read off the home time the heavens were showing. In practice, it was punishing. The measurement demanded a steady hand on a heaving deck, and a single fix could swallow hours of dense calculation, every step a fresh chance for a mistake that would leave you stranded in the wrong ocean. The clock in the sky was real. Almost no one could read it fast enough to trust their life to it. Look at what the sailors were truly asking for. They needed to know what time it was somewhere else, at the very same moment, in order to know where they were. The whole method leans on a single shared instant stretched across the world, the same now that the night sky and the human brain both quietly refuse to keep. They were staking their lives on a simultaneity no one had ever actually proven was there. Without a clock to carry, navigators fell back on disciplined guessing, a method called dead reckoning. You note your speed, your heading, and the time elapsed, and you work out where you must have ended up. On a calm afternoon it holds. Over weeks it rots. A heading off by a few degrees bends your real path away from your drawn path a little more with every mile, and currents you cannot see shove the whole ship sideways without ever touching an instrument. The errors do not cancel each other out. They stack, the way a small bias repeated thousands of times drifts into a large one, until the position penciled on the chart and the ship's true position are simply two different places. The rocks were only the sharpest edge of the danger. A fleet unsure of its longitude planned cautious, wandering routes, adding days and then weeks to every crossing. Extra weeks at sea meant provisions thinning and scurvy creeping through the crew, men dying slowly of a voyage stretched longer than it needed to be by a number nobody could pin down. The missing clock did not only break ships on stone, it quietly lengthened every journey until the sea had time to do its slower killing. When the gap finally bit hard, it bit all at once. On an October night in 1707, a returning English fleet, certain of its position, ran straight onto the rocks of the Scilly Isles off the southwest tip of Britain. 4 ships went down in the dark. Somewhere between 1,400 and 2,000 sailors drowned in a single night, in no small part because no one aboard could say for sure how far west they truly were. Within a few years, a fortune would be placed on the table, a reward worth more than most men earned in a lifetime, for anyone who could finally solve longitude. What stays with me is how quietly the danger sat inside something so ordinary. Not knowing where you are sounds like a failure of maps or of nerve. It was really a failure of timekeeping, a missing number on a dial, and that missing number was enough to swallow whole crews. A man could be healthy, skilled, brave, well-supplied, and still be lost in the deepest possible sense, because the one thing he could not hold on to was the time and a place he could no longer see. Your body comes equipped to sense a great deal. It reads up from down through fluid shifting in your inner ear. It judges near and far, hot and cold, the pull of the ground beneath you. It has no instrument at all for absolute position on a turning world, because there is nothing local left to measure. Your place east or west is not a property of the spot you are standing on. It is a relationship between 2 clocks, and one of them is always somewhere else. To be lost at sea was to be cut off from the second clock, holding only your own time, with nothing to hold it against. Every road back to safety ran through the same locked door. Solve the clock, and the ocean opens and tells you where you are. Fail to solve it, and the most advanced ship in the world is still feeling its way blind across the dark. If your place in the world is really a question about time, what clock could a ship ever carry that the ocean could not break? The answer, when it finally came, was not a better clock for the ship. It was a clock no ship would ever have to carry. If the trouble was holding on to the time in a place you could no longer see, then the cure was to find a clock that everyone, everywhere, could see at once. And there was exactly one place to hang a clock like that: the sky. In 1616, Galileo proposed using Jupiter's moons to do it. He had been watching them for years by then, and he knew their habit intimately. The innermost large moon, the one we now call Io, swings around Jupiter and on each lap slides behind the planet into its long cone of shadow, vanishing from view, then later emerging back into sunlight. Each disappearance and each reappearance is a sharp, definite event. The same event seen by anyone watching that night. A tick of an enormous clock, posted in the heavens for the whole hemisphere to read. Set that against the clocks people could build, and the strangeness of it lands. Every mechanical clock keeps time by fighting decay. A spring unwinds, a pendulum swings, and friction, temperature, and the jolt of a moving deck all conspire to throw it off. You have to wind it, correct it, baby it. Io keeps time by falling. Its orbit is held by Jupiter's gravity and its own momentum, and nothing about salt air or a pitching hull or a cold night reaches up to touch it. The clock runs on the weight of a planet, and it has been running, untended, for longer than there has been an ocean to be lost on. The deeper trick is why the same tick serves everyone. A clock on your wall only you can read. Io's eclipse is not a reading at all. It is a physical event happening out there, the moon truly entering shadow. So a sailor off the coast of Brazil and an astronomer in Paris are watching the very same moment unfold. Compare the two, and you compare two places against one shared instant, which is precisely what longitude demanded, as long, that is, as the tick reached every eye at the same time. Hold that thought lightly. It is doing more work than anyone realized. Io was the right moon for the job, and not by accident. Being the closest of the large moons, it has the shortest orbit, completing a lap in about 1 day and 18 hours. That means a fresh tick comes around constantly. Hundreds of eclipses in a single year, where a slower moon would offer only a handful. And because Jupiter is so vast, its shadow is a hard-edged wall of darkness. So little Io does not fade out gradually. It plunges across the boundary in minutes, snapping from bright to gone, a clean edge you can time to within seconds. A clock is only as good as the sharpness of its tick, and this one ticked sharp. The reason it ticks so faithfully reaches back to that locked rhythm between the inner moons we met earlier, the lockstep, where each completes a tidy whole number of laps against the next. That arrangement is self-correcting. If a moon drifts slightly off its beat, the gentle, repeated tug of its neighbors nudges it back. The result is a regularity that has survived for billions of years and will outlast every empire that ever tried to use it to draw a map. So the work became a matter of writing the schedule down. At the observatory in Paris, Giovanni Domenico Cassini tracked Io eclipse after eclipse, pinned down its average period to better than a minute, around 1 day, 18 hours, and 28 minutes, and carried that rhythm forward to predict the exact Paris time of eclipses months ahead. With those tables in hand, the rest was arithmetic. Note the moment Io vanishes by your own local time, look up the moment it was due in Paris, and the gap between them, multiplied by 15 degrees an hour, hands you your longitude. The lost finally had a way home. On solid ground, it worked beautifully. Surveyors fanned out across France carrying these tables and corrected the map of the kingdom for the first time. And the corrected France turned out to be noticeably smaller than the old maps had claimed, its coastline pulled inward by hundreds of miles of accumulated error. The king is said to have remarked, half in jest, that his astronomers had cost him more territory than any invading army. A moon more than 360 million miles away, far enough that driving to it without stopping would take you something like 700 years, had just redrawn the borders of a country. At sea, where it was needed most, it failed. Reading Io's eclipse means holding a telescope on a single point of light and waiting, sometimes for an hour, for the instant it disappears. On a deck that rolls and heaves with every swell, keeping a faint moon centered in a narrow tube is close to impossible. The clock that no storm could break still could not be read by a man standing in the storm. It would take another century, and a stubborn carpenter building mechanical clocks that could finally survive a voyage before the sailor got his own answer. The sky clock saved the mapmaker. It left the sailor where it found him. There is something I find quietly remarkable about all of this. The most dependable timekeeper within human reach for generations was one that no human had built, could wind, could stop, or could touch. People did not make this clock. They noticed it, learned its rhythm, and copied the numbers down. The universe was already keeping time with perfect indifference, and we simply leaned in close enough to read the dial. The whole method rested on one silent assumption, the one I asked you to hold on to, that the tick of the clock, the moment Io vanishes, reaches all of us at the same instant, that when the moon enters shadow, every eye in the hemisphere registers it together. Sitting inside that assumption, unnoticed, was a number. If the light carrying the tick took any time at all to cross the gap from Jupiter, then the clock everyone trusted was not quite saying what they thought it said, and how late it ran would be set by the one speed we met at the very start of all this. The speed of light was hiding inside the cosmic clock the whole time, waiting for the clock to give it away. If the exact value of that speed sits buried inside this clock, why should the universe have chosen that one value and not some other? For the speed of light to step out of hiding, the clock first had to misbehave. And for a while it did not. Cassini's tables, freshly drawn from years of patient watching, predicted Io's eclipses to the minute, season after season. The method worked, the maps improved, and the assumption underneath it all sat quiet and unexamined. Then, slowly, the predictions began to slip. To build the tables, Cassini had done something that sounds unremarkable and carries a hidden trap. He measured the average time from one eclipse to the next, about 1 day, 18 hours, and 28 minutes, and marched that interval forward, eclipse after eclipse, into the future. Multiply a steady rhythm by a count, and you can name a tick years ahead. The trap hides in the word steady. The arithmetic assumes the only thing standing between you and the next eclipse is time. It quietly takes for granted that the space you are peering across never changes. For most of history, astronomy described the sky after the fact. These tables predicted it, named the exact minute of an event that had not yet happened, and were proven right again and again. That power is intoxicating, and it carries its own blind spot. A method that has been right 1,000 times earns a kind of trust that makes the first failure look like a slip in the observation rather than a crack in the idea. The better the tables performed, the easier it became to wave away the moments they did not. But the space between the planets does change, constantly, and the tables had no room for it. Across a season, the predicted eclipse times started arriving late. Not wildly, a handful of seconds at first, then more, the moon slipping a little further behind schedule each cycle as the weeks went on. Months later, the slippage reversed. The eclipses crept back toward their predicted times, then began arriving early, running ahead of the tables by minutes, before swinging late again. The clock that gravity kept so perfectly appeared, on paper, to be speeding up and slowing down on a yearly cycle. When the astronomers laid the errors against the calendar, a clean pattern surfaced, and it had nothing to do with Jupiter. The eclipses ran latest when Earth was on the far side of its orbit, drawing away from Jupiter. They ran earliest when Earth swung back toward it. And at the one moment each year when Earth passed directly between the Sun and Jupiter, sitting at its closest, predictions and observations fell back into perfect agreement. The clock was not tracking anything about itself. It was tracking us, The size of the error depended entirely on where the Earth happened to be standing. There is something deeply odd in that result, and it is the clue that matters most. A moon hundreds of millions of miles away has no way to know where Earth is sitting, and no reason to adjust its orbit to suit us. Jupiter does not consult our calendar, so the effect could not be coming from the source. Whatever bent the timing had to be added on our side of the journey. Somewhere in the long crossing between the eclipse and the eye, the moon was innocent. The trip was the suspect. From one eclipse to the next, the prediction drifted by only a few seconds, far too little to alarm anyone who saw just one. The trouble was that the tables compared hundreds of eclipses over many months, and those few seconds did not wash out. They added in the same direction, cycle after cycle, until the gap had grown to minutes, more than 10 of them at the extremes. Picture reading a metronome through a telescope while the floor beneath you rolls slowly backward. Each beat sounds a hair late, and you hardly notice until an hour on you are badly out of step, not because the metronome faltered, but because you kept drifting away from it. The metronome was Io, ticking as faithfully as ever. The rolling floor was the Earth, carrying the observers steadily farther from the source. Even now, knowing how this ends, I find it hard to fault the astronomers who kept blaming the moon. 3 explanations sat on the table, and from inside any single season they looked almost identical. Perhaps Io's orbit itself was subtly irregular, the clock truly faltering. Perhaps the average period was a touch wrong, and the whole table needed nudging. Or perhaps something out in the gap between the planets was at work. Over a few weeks, a slightly wrong period and a real physical delay produced nearly the same drift. The careful, defensible move, the one most people made, was to assume the model needed patching and to sharpen the numbers. That reflex, to trust the equation and adjust the data, is a very human kind of arrogance, and it is not stupidity. It is the faith that a beautiful piece of mathematics must be right, and that nature will fall back into line if you just refine the arithmetic. One man came closer to the answer than anyone, and then stepped back from it. For a brief moment, Cassini entertained the possibility that light took time to cross the gap, the very idea that would later explain everything. Then he set it aside. It clashed with too much, with centuries of belief that light was instant, and with his own faith in his tables. He chose the cautious road and kept refining the numbers. It is one of the quietly painful moments in the history of science, a man holding the right answer in his hand and judging it too strange to keep. The pattern is what broke the tie, for anyone willing to look at it squarely. If Io's orbit were simply irregular, the errors would wander with the moon, indifferent to where Earth sat. They do not. If the average period were merely a little off, the predictions would drift steadily in one direction, falling further behind every year and never returning. Instead, the error breathes in and out on a yearly cycle, mirrored exactly to Earth's distance from Jupiter, dropping back to zero each time the 2 planets draw closest. No flaw in the moon and no flaw in the arithmetic behaves like that. Only something tied to the changing gap between the 2 worlds could rise and fall in such precise step with it. And the stakes were not academic. These same tables were guiding surveyors and, where it could be managed, ships. A patterned error of 10 minutes is an error of 2.5 degrees of longitude, well over 100 miles on the ground. The anomaly was not a curiosity tucked in a logbook. It was quietly corrupting the very maps the method had been praised for fixing. There was no way to hurry the test, either. You cannot pull Jupiter closer to check a hypothesis or rerun a season on demand. The only way to confirm the pattern was to watch it repeat, orbit after orbit, year after year, while the geometry of the solar system slowly cycled through the same positions and the same errors returned on schedule. Certainty here was not a matter of cleverness. It was a matter of patience counted in years. which narrows everything to one conclusion before any deeper one can follow. Whatever was happening lived in the space between Earth and Jupiter, and it grew and shrank with the width of that space. At its largest, the extra delay matched the light having to cover roughly the full width of Earth's orbit, the entire span of our yearly trip around the Sun. That left two roads pointing in completely different directions. Either the empty space itself was doing something to the signal as it stretched, thickening or bending or slowing whatever crossed it, or the space did nothing at all, and the messenger carrying the tick simply took time to make the longer trip. If the error tracks the distance between two planets, is something happening in the space between them, or to the light itself? Rummer took the second road. The space between Earth and Jupiter was not thickening or bending or meddling with the signal. The space was doing nothing at all. The light was simply taking time to cross it, and as the gap grew wider, the light took longer to arrive. The whisper everyone had been straining to read was not coming from the void, it was coming from distance itself. To see how strange that idea was in its own century, you have to set aside everything you already know. Light, as a thing that travels, that leaves one place and arrives at another a measurable while later, crossing empty nothing at a fixed pace, was close to unthinkable. Light was illumination. It filled a room the instant a candle was lit. The natural suspects, if the timing was off, were all in the gap. Perhaps some invisible substance out there slowed the rays, or refracted them, the way water bends a spoon. Blaming the medium felt safe. Saying that light itself had a speed meant saying the universe imposed a delay on seeing, and almost no one was prepared to say that. The clue that settled it was the shape of the error, not its size. The delay did not just grow as Earth pulled away from Jupiter. It grew in exact step with the distance, doubling as the gap doubled, shrinking back to nothing as the gap closed. That clean proportion is the fingerprint of a fixed speed. If light crosses a mile in some set time, it crosses 2 miles in twice that time, with no exceptions and no curves. A meddling medium has no reason to be so tidy. Something absorbing or bending the light would dim it or distort it, and there was no matching dimming, no creeping discoloration, nothing but a pure, proportional lateness. The numbers behaved exactly as a constant travel speed demands, and exactly as nothing else does. His real move was not the calculation, it was a reframing. Everyone before him had treated each eclipse as a single tick to be checked against a table, asking whether the clock was running true. Romer stopped asking about the clock. He started adding up the journey. Across the months Earth spent receding from Jupiter, every successive eclipse sent its light from a starting line a little farther away than the last. So each arrived a little later than the one before, the lateness piling up not because Io faltered, but because the commute kept lengthening. The error was never in the moon. It was in the road. Watch what happens to the light under that picture, and the whole puzzle from before clicks into place. When Earth swings away from Jupiter, each eclipse's light begins its trip from progressively greater distance. So, the eclipses appear to lag further and further behind schedule. When Earth curves back inward, the trips shorten, and the eclipses bunch up early. At the moment the two planets sit closest, the distance is barely changing from one eclipse to the next, and predictions and observations agree. Every strange behavior the astronomers had argued over, the lateness, the earliness, the perfect alignment at closest approach, falls out of one assumption and one assumption only. Light takes time. And the rival road, the one that blamed the void, quietly closes off. For empty space to fake this result, it would have to act only along the exact line between us and Jupiter, scale its effect precisely with the length of that line, leave no smudge or color or dimming behind, and then somehow behave identically in every direction toward every other object in the sky. You can keep adding rules to the void until it mimics a finite speed, but at some point you are no longer explaining the data. You are just describing a finite speed in heavier language. The simpler statement was sitting there the whole time. None of it shows up in a single night, which is why it took so long and one particular mind to see. The extra few seconds added to any one eclipse is far below what anyone could notice. Only by summing the small delays across an entire season do they swell into minutes, and only across a full orbit does the clean proportion with distance reveal itself. The truth was never hidden in one observation. It was spread thin across hundreds of them, visible only to someone willing to stop staring at the moon and start measuring the changing length of its light's journey. The thing worth slowing down for is not the arithmetic, it is the inversion. For years, the discrepancy had been treated as a flaw to be scrubbed out, an embarrassment in an otherwise elegant table. Romer looked at the same flaw and recognized it as the measurement. The error was not noise sitting on top of the signal. The error was the signal. Everything the astronomers had been trying to correct away was the universe quietly reporting one of its deepest facts, and they had been erasing the report each time it appeared. There is a weight hidden inside that modest claim about a moon, and it reaches much further than longitude. If light takes time to arrive, then seeing is always seeing the past, by an amount set entirely by distance. The eclipse you observe already happened. The sky you map is already old. Romer was not trying to overturn the nature of time. He was trying to fix a clock. But folded inside his small correction was the end of the shared, universal instant. The same loss the night sky and the human brain had been hinting at all along. He carried it without announcing it, the way a single measured fact can carry a revolution it does not mention. Still, conviction is not proof, and Romer knew the difference. His idea explained every past observation beautifully, and explaining the past is the easiest trap in science. A determined skeptic could always answer that the average period had simply been measured a touch wrong, that the whole effect was a leftover error in the tables, and from the existing data alone, there was no way to force the argument shut. You cannot hold light still to inspect it. You cannot catch it halfway across the gap and check its speed. The delay leaves no mark a hand can touch, no needle it moves, nothing you could ever feel. To prove that light runs late, he would have to do the one thing that turns a clever explanation into an undeniable fact. He would have to predict the future and be right. If light is simply arriving late, how late is it? And how would anyone put a number on a delay no one can feel? You prove a delay no one can feel the same way you prove anything you cannot touch. You bet on it in advance. An explanation that only accounts for what already happened can always be doubted, patched, talked away. A prediction cannot. If you can say, weeks ahead, exactly how the universe is about to misbehave, and then it misbehaves on cue, the argument is finished. That was the one move Romer had left, and in 1676 he made it. Standing against him was one of the oldest ideas in human thought. 2,000 years earlier, Aristotle had argued that light does not travel at all. It was not a thing moving from place to place, but a condition, a state. The air fell into the instant a fire was lit, present everywhere at once. The view was not foolish. It matched every scrap of ordinary experience. Open your eyes, and the world is simply there. Nothing in daily life so much as hints at a journey. For 20 centuries, instant was not the lazy answer. It was the answer that fit the evidence. It had even won a real argument to get there. Centuries before Aristotle, the philosopher Empedocles had guessed that light streams outward and takes time to cross a distance. Aristotle weighed that idea and rejected it, on the reasonable grounds that no one had ever caught light arriving late. So the instantaneous view was not a default nobody questioned. It was a position that had beaten its rival in open debate and held the field for 2,000 years, precisely because the evidence kept agreeing with it. Galileo had tried to test it head-on, and the attempt is worth lingering on for what it reveals. He stationed 2 people on distant hilltops, each with a shuttered lantern. One would uncover his light, and the moment the second saw it, she would uncover hers in reply, so that by timing the round trip, he could clock light across the valley. It did not work, and it could not have. Across a mile, light makes the round trip in about 10 millionths of a second, while human reflexes add a fifth of a second of fumbling at each end, burying the real delay under something tens of thousands of times larger. The experiment told him only that light was faster than 2 people with lanterns could catch. A floor, not a ceiling. He suspected light had a speed and could not prove it, because his ruler was a mile long and the thing he was chasing needed millions of them. Rumor's advantage was that he never had to race the light himself. The solar system had already built the apparatus. Instead of 1 mile, he had the width of Earth's whole orbit, a baseline near 200 million miles across, stretching and closing on its own as the planets moved. Instead of a fifth of a second reflex, he had Io's eclipses, sharp ticks he could time across months and pile up into minutes. Galileo had tried to catch light in a foot race. Romer let the cosmos run the experiment at a scale no hilltop could approach, and read the results straight off the sky. There is something worth naming plainly in that shift. For the first time, a fundamental constant of nature was being measured not in a workshop, but in the choreography of planets. The laboratory was the solar system, the ruler was an orbit, and the clock was a moon. No instrument a person could build had a baseline long enough to weigh the speed of light. The heavens did, and they had been offering it freely the whole time, to anyone willing to read the delay as a measurement instead of a mistake. In September of 1676, he stood before the Academy in Paris and made a claim that must have sounded reckless. The next emergence of Io from Jupiter's shadow, due that November, would not arrive when the tables said. It would come about 10 minutes late. He was not correcting a number after the fact. He was staking his name on a moon, hundreds of millions of miles away, running late by a precise amount on a precise night, for a reason almost no one in the room would grant him. The astronomers who trusted the old tables expected the eclipse on time. Rumor told them to wait an extra 10 minutes. On the 9th of November, they watched. The tables ran out, and Io's edge stayed dark. A minute passed, then several, then close to 10, and only then did the moon slip back into the sunlight, almost exactly when Romer had said it would, and almost exactly when everyone else had said it would not. The explanation that had merely fit the past had now reached into the future and bent it correctly. There is no stronger thing a scientific idea can do. The delay no instrument could feel had announced itself, right on schedule, to a room full of witnesses. Accepting it meant accepting something far heavier than a corrected table. If light is late, then every observation an astronomer ever makes is a look backward, the heavens delivered as a delayed broadcast rather than a live one. The prediction did not only fix the clock, it quietly turned the entire night sky into a recording of things that had already happened, and there was no way to take that consequence back once you had taken the prediction seriously. From the accumulated delay, Romer could finally put a duration on the thing. The time for light to cross the full diameter of Earth's orbit, that span of roughly 186 million miles, came out near 22 minutes. Hold that distance in your head for a moment. A car driving without rest, day and night, would need more than 300 years to cover it. Light crosses the same gap in about the length of a quiet walk. His 22 minutes ran a little long, partly because the true size of Earth's orbit was not yet known. The modern figure sits closer to 17. The exact value was almost beside the point. For the first time, light had a measured travel time at all. He had a duration, not yet a speed you could write in miles per second, and turning the one into the other would fall to someone else. The room was persuaded. The world was not. Being right in public did not end the argument the way you might hope. Cassini, whose tables had just been unseated, never fully accepted it, and much of the establishment clung to the old view for decades. A correct prediction can always be dismissed as luck, and it was. The matter was not truly settled until more than 50 years later, when an English astronomer named James Bradley, chasing an entirely different question, stumbled onto a second, independent fingerprint of light's finite speed hidden in the faint yearly shifting of the stars. Two unrelated roads arriving at the same number is what finally shut the door. The truth about light's speed did not land all at once. It arrived the way light itself does, taking its time, reaching different minds years apart. The detail I cannot get past is the waiting. Picture Romer on that November night, having told an unconvinced room that a moon would be 10 minutes late, with nothing left to do but stand in the dark and wait to be proven a fool or a prophet, while the very thing he had wagered on, the slow arrival of light, played out in front of him at the exact pace he had claimed. He had bet everything on the universe being honest about its own delay, and then he had to live through that delay in real time, second by second, the truth crawling toward him at precisely the speed he had just discovered. What he had shown reached past any clock or coastline. Light was late, measurably, even across the small neighborhood of our own sun. But the only place he had ever checked was here, in this one corner, with these two worlds. The stars sat unimaginably farther out, in regions no eclipse and no telescope of his could probe, and he had no way to know whether the rule he had caught at home held anywhere beyond it. If light runs late even across our own solar system, is its speed the same in every corner of the universe we will never reach? You cannot ask whether light's speed is the same everywhere until you can say what its speed is here. And after Romer, you still could not. He had handed the world a time, about 22 minutes, for light to cross the width of Earth's orbit, and a time is not a speed. To turn one into the other, you divide the distance by the duration. The duration he had. The distance was the problem. What Romer had actually measured was a ratio buried inside the solar system. Light crosses one width of Earth's orbit in so many minutes. That tells you how light speed compares to the size of our orbit, and nothing else. To reach a figure in miles per second, you have to know how many miles wide that orbit truly is. In 1690, almost no one could say. The absolute size of the solar system was one of the great open wounds of astronomy. The planets' distances were known in proportion to one another with real precision, the whole system mapped to scale, while the single number that would convert any of it into miles stayed out of reach. The trouble is that you cannot lay a tape measure across space. The only handle anyone had was parallax, the tiny shift in a planet's position against the background stars when you view it from two far-apart points on Earth at the same moment. The nearer the planet, the larger the shift, and from the size of that shift, you can triangulate the true distance. A few years before Huygens set to work, astronomers had aimed this method at Mars, observing it from Paris and from the coast of South America on the same nights, and wrung out a first rough scale for everything. The angle they were chasing was minute, smaller than a coin seen from across a field, and a slight error in it threw the size of the whole solar system off by millions of miles. The number everything depended on was the number hardest to catch. Everything downstream hung on getting that one distance right. Astronomers carried a precise scale model of the solar system in their heads, every orbit sized against every other, a model with no real ruler attached to it. The Earth-to-Sun distance was that missing ruler. Pin it down, and the whole model snaps to true scale, every planet, and later every star, fixed to honest miles. Get it wrong, and the entire universe comes out the wrong size by the very same factor. Christian Huygens took what little there was and did the division anyway. Around 1690, holding Römer's travel time in one hand and the best guess at the orbit's real width in the other, he became the first person to write down an actual speed for light. The figure he reached was over 200,000 kilometers every second, more than 120,000 miles a second. A number, at last. Not a feeling, not a philosophy. Not the word instant, a specific quantity you could carry into other calculations, test against the world, and one day correct. It was wrong, and by a wide margin. The real speed runs close to 300,000 kilometers a second, about 186,000 miles, so Huygens landed roughly a third short, dragged down by Römer's overlong timing and an orbit still measured too small. The striking thing, and it is worth saying without dressing it up, is how little that error mattered. Being a third wrong about the speed of light was an enormous stride forward, because the day before there had been no number to be wrong about. Light had been a quality of the air for 2,000 years. Now it was a measurement with an error bar, which is the exact shape a fact takes when it finally joins physics. Once light had a speed, the number quietly began doing something far larger than describing light. It became an exchange rate between distance and time. A currency rate ties two separate things together, so any amount in one can be read straight off in the other. The speed of light does that for space and time. Every distance in the universe can now be quoted as a duration, the time light needs to cross it, and every such duration converts cleanly back into a distance. The sun stops being 93 million miles away and becomes 8 minutes away. The width of our galaxy is not a number of miles you can hold in your head at all. It is 100,000 years. We stopped measuring the cosmos in lengths and started measuring it in weighting. We never stopped speaking in those terms. When you hear that a star is 4 light-years away, or that a signal from a distant probe is 20 light-minutes out, you are using this discovery as a ruler. The unit itself, a distance named after a span of time, only makes sense if light holds a fixed speed. Every time anyone maps the sky in light-years, they are quietly repeating what Römer found in a moon and Huygens turned into a number. That same number is the wall from the very start of all this. Writing it down did not only free light from philosophy, it set the exact dimensions of the cage. Everything lives inside. The speed of light is the fastest that any signal, any influence, any scrap of news can travel. So the moment you fix its value, you fix the tempo of cause and effect across the entire universe. A command sent to a machine near Mars takes minutes to arrive, and minutes more for any reply, which makes a real conversation across that gap impossible, not from any weakness in our technology, but from the number itself. The figure that let light step into physics is the same figure that locks every one of us inside a finite reach. 3 centuries on, physicists came to trust that number so completely that they turned the whole relationship inside out. They stopped measuring how fast light travels and instead fixed its speed by definition, then used it to define what a meter even is. Distance became the derived thing, and the speed of light became the bedrock everything else is measured against. The exchange rate that Huygens scratched out, a third too small, eventually stopped being something we measure at all and became the standard the rest of the universe is weighed by. I used to think the hero of this story was Römer, and the longer I sit with it, the more it looks like the size of an orbit. Romer found the delay, and that was the daring part. But the delay alone gives you proportions, a universe measured only against itself. The leap into real miles and seconds waited on someone managing to gauge the plain physical width of our own backyard, the distance to the sun, against the impossibly faint wobble of Mars among the stars. The most universal number we have could not be written down until we first knew, in honest miles, how far it is to our own star. Hold the corrected number for a moment, the true one. Light moves fast enough to cross the United States, coast to coast, about 20 times in a single blink of your eye. At that pace, it spans the gap to the moon in just over a second and reaches the sun in 8 minutes. Inside our own solar system, that ferocious speed still only ever adds up to minutes of delay, a few here, a few more there. But the same number, unchanged, has to carry light across distances that dwarf the solar system the way an ocean dwarfs a single raindrop. If one number rules how fast light crosses our own solar system in minutes, what does that same number become when light has to cross the entire universe? Across the solar system, the delay was minutes. Step outside it, and the minutes break open into something with no floor. The nearest star beyond our sun is so far that its light spends more than 4 years on the way, so you see it not as it is, but as it was 4 years back. The center of our galaxy is 26,000 years behind. The light from the Andromeda Galaxy, the farthest thing most people can find with the naked eye, set out about 2.5 million years ago, before our species existed in anything like its present form. Reach for the most distant galaxies in our deepest images, and the light is well over 13 billion years old, sent when the universe itself was new. The same number that cost Cassini a few minutes now costs us the whole history of humanity. And that is only the next galaxy over, which turns every glance at the sky into an act of looking backward. The night sky is not a photograph of the universe as it stands. It is a single image stitched together from thousands of different epochs, each point of light frozen at whatever moment its light happened to leave. You see the nearby stars as they were a few years ago, the far ones as they were when mammoths walked, the distant galaxies as they were before the Earth had formed, all of it laid side by side on the same dark dome as though it belonged to one instant. It never did. The deeper you look into space, the deeper you are looking into time, and there is no way to pry the two apart. This is why a star can be gone and still hang there shining for you. Take Betelgeuse, the red shoulder of Orion, about 600 light-years away. If it collapsed and detonated tonight, you would keep seeing it sit calmly in the sky for another 6 centuries before the news of its death arrived. Turn that around, and the unease lands. It may have already exploded, sometime in the last 600 years, and we would have no way of knowing, because the light carrying that event is still somewhere out there in transit. The Betelgeuse you can point to on a winter night is not a fact about the present. It is a rumor 600 years old. It would be easy to file all of this under a quirk of slow signals, a delay in the mail that leaves the real present out there intact even if we receive it late. That is the part Romer's discovery, carried to its end, takes away from us. Because the speed of light comes out the same for everyone, no matter how they are moving, there turns out to be no single shared present stretched across the universe at all. Not one we receive late. Not one at all. The instant you call now, here, cannot be matched to a unique instant happening now over there. Different observers, moving differently, sort distant events into now, and not yet in truly different orders, and none of them is mistaken. There is a thought experiment that makes this unbearably concrete. Picture 2 people passing each other on a sidewalk, one strolling toward Andromeda, the other strolling away, at nothing faster than walking pace. Their disagreement about what is happening on Andromeda right now is not a fraction of a second, because Andromeda lies 2.5 million light-years off. That tiny difference in motion fans out across the gulf into days. For one of them, a fleet might be launching there at this moment. For the other, that same launch sits still in the future, or already in the past. Two people on the same pavement, agreeing on everything they can touch, hold two different presents for the same distant world, and physics sides with both. The universal now the lost sailors staked their lives on was never out there to be found. The reason it fractures is stranger than slow mail. To say two distant events happen at the same time, you have to synchronize clocks, and the only tool for that is a signal, which travels at the speed of light. If that speed is the same for everyone, regardless of their motion, then people moving differently are forced to disagree about which faraway events line up with their own now. Now is not a single sheet laid flat across the universe. It is a slice each observer cuts through space and time, and the angle of that slice tilts with your motion. The sidewalk pair's disagreement is just that tilt, magnified across millions of light years. Push the looking back to its limit, and you reach a wall. The universe is about 14 billion years old, so light has only had 14 billion years to travel toward us, and anything farther than light could have crossed in that time has simply not arrived. We sit at the center of a sphere of received past, an edge marking not where the universe stops, but where its light has not yet reached us. Beyond it, more universe almost certainly exists, sending its light our way, still on the road. Each year the sphere widens a little as older, more distant light finally finishes its trip. And the wall hides more than old light. The patch we can see is almost certainly a small piece of something far larger, perhaps endless, and most of it sends light we will never receive. The expansion of space is carrying the most distant regions away so fast that their light will never close the gap to us, however long we wait. There are places whose present is sealed off from ours for good, not by distance alone, but by a universe stretching faster than light can cross it. We will never see them as they are, and past a certain point, we will not see them at all. The faintest, oldest light of all is already here, and it is everywhere. About 14 billion years ago, not long after the beginning, the young universe cooled enough to turn transparent and let go of the light that had been trapped inside it. That light has been traveling ever since, stretched and dimmed by the expansion of space until it now reaches us as a faint hiss of microwaves falling from every direction at once. It is the closest thing there is to a baby photograph of everything, and a small fraction of the static an old television once caught between channels was exactly this, the first light of the cosmos ending its 14 billion year journey in a living room. It is also a curtain we cannot see behind. Before that moment, the universe was a dense fog, and light could not move freely through it, so there is no older light to catch. That faint glow is the earliest image the cosmos will ever hand us, a wall of light beyond which sight itself fails. Everything before it stays hidden behind the fog, reachable one day, if at all, only by messengers other than light. Here is the plain shape of it, said without softening. Everything you will ever see, you see in arrears. The sun by 8 minutes, a friend across the room by a few billionths of a second, the stars by years, the galaxies by eons, with no exception anywhere, no object close enough to reach you in true simultaneity. You are sealed inside your own present, receiving only the past of everything else, forever a step behind. That is the tragedy folded into a finite speed. It is also, oddly, the only reason the deep past survives at all. The same light that separates you from everything is the light that keeps history from vanishing, holding every moment in flight somewhere, still on its way toward an eye that has not yet received it. There is a version of this I can follow on paper and still cannot make my body believe. I understand why there is no shared now, why two people on a sidewalk can hold different presents for Andromeda, and the understanding does nothing to loosen the bone-deep certainty that of course the universe is all happening at once, together, right now. The intuition does not break, even after the physics does. And yet every example I have reached for has been far away, out among the stars, where the delay is easy to grant. If every light you have ever seen left its source in the past, what about the light reaching you in this room, right now? The light in this room is old too. Smaller, by an unfathomable margin, but old in exactly the same way. The glow from the lamp left its surface a few billionths of a second before it touched your eye, so even the room you are lying in reaches you a little after the fact. Nothing changes at this scale except the size of the delay. The principle that pushed Andromeda 2.5 million years into your past is the same one working here, in the short gap between a lamp and your face, quietly, every waking moment. We started with that lamp, already in the past, and it has been true the whole way through. Everything in between, the lost ships, the moon that kept time, the moon that ran late, was only that one small fact about a bedroom, followed outward until it reached the edge of what can be seen. If any sunlight fell on you today, the delay runs far deeper than the 8 minutes from the sun's surface. The energy in that light was made in the sun's core, in a furnace so dense that a packet of it cannot simply fly out. It is absorbed and thrown back, absorbed and thrown back, taking a tiny random step each time, wandering a tangled path through the layers above it. What reaches the surface is not the same photon that started, but energy handed along a vast relay, cooled from fierce radiation down to ordinary light. By most estimates, that crawl from core to surface takes something on the order of tens of thousands of years, though the figure is hard to pin and still argued over. The warmth on your skin this afternoon carried energy that began its escape from the center of a star while the last ice age still held the Earth. The 8-minute flight across space was the quick part. The lag does not stop at your eye either. The room you are sensing now is assembled a fraction of a second after the light and sound arrive, put together by a brain that always runs a little behind the world it describes. Once this might have sounded like a separate quirk of biology. It is the same story scaled down to nerve fibers, a finite speed, a signal in transit, a present that lands late. The universe runs the identical delay from the far edge of the observable cosmos down to the inside of your own skull, changing nothing but the distance. And your eye is where some of that light's long journey simply ends. When a photon strikes the back of your eye, it is absorbed by a single molecule that bends in response, and the light is gone, spent, its travel over for good. The starlight that crossed years of empty space, the lamplight that crossed a room, both finish in the same place, swallowed by the cells that let you see them. To look at anything is to be the final stop on a trip that may have taken an instant or an age. You are where light comes to rest. There is a quieter way to hold everything this has been circling toward, and I think it is the truer one. A finite speed of light can sound like an exile, as though you have been shut out of a real present happening somewhere without you. But there was never a shared present to be shut out of. The universe does not keep one. You were not cast out of the moment. You have always lived precisely where you are, inside a present that is slightly late, entirely local, and completely your own. There is nothing on the far side of the delay that you are missing, because the delay is not a wall between you and the real now. The delay is what now is made of. The same patient universe that delivers starlight late is the one that built you, and it took its time over that as well. The calcium holding your bones together, The iron riding in your blood, the oxygen moving through you in the dark, none of it was made on Earth. It was forged in the cores of stars that lived and died before the sun existed, flung across space when they collapsed, and slowly gathered into the cloud that became this planet and everyone on it. You are not watching the old universe from the outside. You are a piece of it that cooled and gathered, and learned to ask how far away the stars are. The history is written right into your chemistry. The hydrogen in the water you drank tonight came straight from the first minutes of the universe, older than any star. The carbon in your skin and the oxygen in your lungs were cooked in the hearts of dying suns, and the trace of iodine your body needs to think and to rest was likely made in something far more violent. The collision of two dead stars, an event so extreme it scatters its debris across whole galaxies. You are an assembly of three separate eras of cosmic history, walking around, breathing, listening to this in the dark. And the traffic does not run only one way. You are not only receiving light, you are giving it off. Right now, in the dark, your body is glowing. Not in any color your eyes can catch, but in infrared, the warmth radiating off your skin streaming outward as light at the same fixed speed as everything else. Some of it sinks into the walls, some slips out a window and keeps going, past the roof, past the air, out into space, carrying the faint record of this exact moment away from you at 186,000 miles a second. The light reaching you tonight is the deep past of distant things. The light leaving you tonight is becoming the distant past of somewhere else. This is not a figure of speech. A thermal camera in this room could see you shining at this instant, and the heat you are shedding into the night does not stop at the window. The part that escapes simply travels, on, until something far away and far in the future finally absorbs it. The record of you lying here, quiet and curious at the end of a long day, is leaving the planet as you listen, joining the same endless flight of old light we have been following the whole way. You are a sender now, not only a reader. Which is, in the end, a strangely gentle thing to know. There is nowhere the present is happening more truly than where you are. No reeler now to chase, no instant you are being kept from. The light that left you a moment ago is already gone. The light arriving now is already old, and somewhere between the two is the only place anyone has ever lived. You do not have to hold on to any of it. The light does the holding. It carries every moment outward on its own, whether or not you reach for it, the way it has carried a moon's eclipse, a dying star, the first glow of the cosmos, and the warmth leaving your skin tonight. All of it still traveling, all of it on its way to some eye that has not seen it yet. The light on your skin tonight already belongs to a moment that is gone. So when, exactly, are you living? There is nothing left to work out before sleep. The question can stay open. It has stayed open for more than 300 years, and it kept good company the whole time. Thank you for spending this stretch of the dark here, following one small lateness in a moon all the way out to the edge of the visible and back to the warmth of your own hands. Let the light keep doing its quiet work without you for a while. Let the present be as late and as local, and as yours as it has always been. Rest now. The old light will still be arriving in the morning, and so will you.